Welcome to lesson 2.4. This one is looking at continuity, and then we get into this word of differentiability. Is a function differentiable? Can we find the derivative? So that's the topic. Let's get into it. A little bit of review on continuity. If a function f of x is continuous at x equals c, then what would we know about our function? Well, in order to be continuous, we knew the left and the right limit had to be equal to each other so that the limit existed. And we had to know that, oops, getting some pop-ups, f of x, or no, f of c exists so that the point exists. And then we need the limit as x was going towards c of f of x was equal to f of c. The point was equal to the limit. So that was continuity. In essence, a function is continuous at x equals c when you can draw a graph without lifting the pencil or stopping. So I have this nice continuous graph that I never have to lift my pencil for. Differentiability. Sounds like a made-up word, doesn't it? We do that a little bit in math. So we say that a function is differentiable at x equals c if the slope exists, meaning there's a derivative there. For a function f of x to be differentiable at some point, x equals c, then two things must be true. F of x must be continuous at x equals c, so no, jumps, holes, vertical asymptotes, those ideas. And the derivatives from the left and the right sides as x approaches c must approach the same value. So here we're talking about the slopes from the left and the right side of our curve must match up in order to be differentiable. Graphically, the slope must approach the same value from both sides. So an AP exam tip when looking at a graph, look for any x values where the function's not continuous or has a sharpish corner. So I see some sharp corners down below. Or it has a vertical tangent line. And it looks to me like we have all of that going on in this graph. This is a crazy busy graph here. So example 1, find all the values of x where the function f of x is not continuous. Classify each continuity or discontinuity as removable or non-removable. So a little practice from unit 1. All the functions where it's not continuous. Well, the first thing that grabbed my eye was this hole. And the other thing that captured my eye was this jump going on. Oh, there's one other thing that just struck me. And that is, at about this point, I would end up with a vertical tangent line, wouldn't I? So let's talk about which ones are removable and which ones are non-removable. The removable, of course, is the hole, excuse me, at x equals -2. You can put hole behind it if you want, just to sink that thought in our head. And then it's non-removable. Looks like at x equals 5. What type of discontinuity do we have there? Starts with a J, jump discontinuity. And then at x equals, I'm going to say 7. Oh, but that is, hold off on that thought. That actually is going to be down in differentiability because we aren't hitting like a vertical asymptote there. Whew, I was messing that up. So we just pick up those two things right now. Example 2, we're going to pick up that vertical. Find all the values where the function above is not differentiable. So look for sharp corners. Boom, boom. How many do you see? I saw 3. So sharp corners. X equals -9, -6, and +2. And then discontinuities That happens at the two that we listed above, at x equals -2 and 5, because if it's not continuous, it's not differentiable. Okay, and then lastly, where did we see that vertical tangent line? This is that one I was talking about earlier. It is continuous there, right? We wouldn't have to lift our pencil, but it will not be differentiable. Why won't it be differentiable if I have a vertical tangent line? Well, if I think about change of y over change of x for our slopes, the y value is changing around that, but the x value is not. And so we'd have, some value up on the top, but we'd be dividing by 0, and that's going to give us an undefined slope. So that's why it's not differentiable at a vertical tangent line. All right, moving on. Example 3. Consider the function g of x. Find the following values, if possible. G of -4. Pay particular attention to primes and no primes, right? G of -4. 1, 2, 3, -4. I'm going to call that 1. Is that what you call it? G prime of -4. Now we're talking about the slope, aren't we? And I can tell that this is the point -2, 0. So it looks like this drops by 2 right by 4. 1, 2, 3, 4. Drops by 2. So it went down 2 right 4. Looks like I get a -1/2. It's a nice linear function at that point. So finding the tangent line at -4 was easy. It just followed the line perfectly. So then I just used, change of y over change of x idea to get that particular slope. G of 3, go to 3. Oh, they even gave us the point, didn't they? It is a 2. The y value is a 2. G prime of 3. Ooh, that's a little tricky. The limit coming in from the left of 3 for G prime would be this positive slope. Looks like it goes up 3 over 1 is 3. The limit as x comes into 3 from the right of G prime of x is going downward, isn't it? So what's its slope? Let's use a different color. It would be down and right, 2 and 2. It looks like it's a slope of 1 then. So down 2 over 2, which would give me -1. Do those limits of the derivative agree? They do not. 3 does not equal -1, and therefore we must say this is undefined. So here's kind of the formal analysis that I did for my slope on each side of the value c equals 3. And notice that the slopes weren't the same. It was quite easy, wasn't it? This was a positive slope. That was a negative slope. We knew they weren't going to be equal. Let's move to g of -2. G of -2 sits right there. And it looks like its value is 0. Erase this. G prime of -2. G prime of -2. Well, this was a slope. We calculated this one out earlier. This was a -1/2 slope, wasn't it? And then it goes into a much steeper slope. The slopes are not equal. This would have to be undefined. It hit that sharp corner, didn't it? And we know that functions will not be differentiable when we hit a sharp corner. Much like the sharp corner, you might even want to make that note on 3. We hit that sharp corner and it's an abrupt change of slope then. And that's not good. We need a nice soft transition. G prime of 2, G prime of 2. Oh, look at, we're hitting another sharp corner. G prime of 2 is undefined. We shouldn't say equal. It's just undefined. It's hard to be equal to something that doesn't exist. And G prime of 4. 4 sits right there. That looked like down 2 over 2, didn't it? That was a slope of 1 being negative. All right. Hopefully that made sense. Down below, the graph H prime is shown. The graph H prime, use the graph to find the following. So now, oh my goodness, we are looking at what graph? The derivative graph. Different than the original function graph. This is tricky. You got to shift your mind a little bit. So I am looking at the derivative graph. H prime of -1 is a 3. H prime of 1 is 1. Because when I read this graph, I'm reading it kind of at face value, and it's giving me H prime because that is the graph I'm reading, H prime. So it's just face value. H prime of 2, ooh, doesn't exist, does it? Let's say undefined, not. Does not exist is really reserved for limits. H prime of 4, give that a half, wouldn't you? H prime of -5, I'd give that a 1.5. Maybe I would, oh, it's a -3/2. I was just saying, maybe I'll write it as a fraction. H double prime, ooh, that's a new symbol for us. H double prime means the second derivative. Or I can interpret it, or the slope of H prime of x. Okay? Because if I look at the slope of H prime of x, how is H prime changing? What's the rate of change of H prime? That gives me H double prime. So I want to look at how fast is H prime changing. So now I am reading the slope of -5. It looks like it goes down a half and over 2. Down a half over 2. Down would be negative. And then I multiply by the reciprocal. Looks like this is a 1/4 slope that is negative. H prime, now we're back to reading face value, aren't we? H prime of 3 is 1. H double prime of 3 hits a sharp corner. Is there a derivative? No. This would be undefined. I'll take off the equal sign. This is undefined. H double prime of -1. Well, let's find -1. H double prime means read the slope of it. So I'm looking at the tangent line that has a 0 slope. So slope of H prime of -1 is what we did to get that. You might want to make a note to yourself. H double prime of 4. H double prime of 4. So now I want to know, how is my function increasing or decreasing at 4? So H prime looks like it's going, what was it moving? Up 3 over 2. This will be 3 halves. H double prime at 2. Down 1 over 1. That's a -1. And that is the slope of H prime of 2. H double prime of 1.17. How am I supposed to be able to calculate that? That's a terrible number for me to calculate. But it's a linear function in that region, so it's going to be the same slope that we had at 2, -1. Okay, the main practice on this is really paying attention to the prime symbol. Is it 1' or 2'? And also keeping in your mind what graph you're reading. Here we read H', and on this one, this was just straight up g of x. So it read about the function. And then when I read the slope of this, the slope of g of x, that informs me about g' of x, doesn't it? I hope you're catching on to this. It's a little bit tricky, but you'll get it. We practice this a lot. The theorem that talks about differentiability, it tells me differentiability implies continuity. If f is differentiable at x equals c, then I know for sure it was continuous at x equals c. Remember when we started this game today, we looked for those places of discontinuity because we knew that our functions would not be differentiable where we had discontinuities. So that is this theorem in a nutshell, which if I do the contrapositive statement, which says not Q, then not P, well, maybe I should talk about P leads to Q, right? Differentiable means it's continuous. If I look at it in reverse and contra, negating it, I get if f is not continuous, then it's not differentiable. So I like to remember these two statements. We got a true or false statement here. The converse to the theorem above is also true. What would the converse say? It would say, if continuous, then differentiable, because we just switch our P's and Q's around. That would be false. I could have continuity and hit that sharp point, and that is not differentiable. So sharp corners are not differentiable, yet they are continuous. Okay? Some logic thinking there. Glad you did so well in geometry so that you got that. All right, so there's a worksheet to do. Hopefully it follows along quite similar to the work that we just did in our notes. Have a wonderful day.